Hello, we are Group 34. Our project focuses on exposing fake COVID-19 news, and this is our final presentation. While social media enables a great amount of communication, it also enables the spread of false information. We have seen over the past 9 months that this is particularly true when it comes to news regarding the COVID-19 pandemic. Our team's ultimate goal with our project has been to create a system that can automatically detect fake news as it pertains to the coronavirus. Throughout the project, we accomplished many different subtasks with this goal in mind. These components mainly consisted of preparing our data, implementing unsupervised learning algorithms, likewise with supervised learning algorithms, analyzing the results through performance metrics, and visualizing the outputs. The graphic here represents a visualization of the process we followed when working through the phases of the project. Inside the red box, you can see the steps we took to accomplish the unsupervised learning portion, with an emphasis on gathering and cleaning our data, vectorization, principal component analysis, and clustering with visualizations of the results. Data gathering and cleaning involved scraping relevant tweets for our dataset and removing faulty data points. To vectorize this dataset, we employed the TF-IDF algorithm, which we then used in principal component analysis to reduce the dimensions significantly. We chose to utilize clustering with k-means and dbScan implementations, and using the outputs, we were able to graph word-class correlations.
We performed some initial exploration of the dataset by looking at the class imbalance between true and fake tweets. We found a significant imbalance of 88% true to 12% fake. We later resolved this imbalance by oversampling the fake data points. We also performed dimensionality reduction using the PCA algorithm. We performed PCA on the vectorized tweets and calculated the cumulative explained variance for each PCA component. Through this method, we were able to capture 99% of the variance in the original dataset using only 314 PCA dimensions. This reduced the dimensionality by more than half. We then created two visualizations to further explore the data. The left shows the words that are most strongly correlated with each label, true or false. This gives us a qualitative feel for the topics covered by each label. The visual on the right plots each point on a 2D graph where the X and Y axes represent the first two PCA components of each point. This graph shows a clear visual distinction between the true and false labels, which portends well for our classification efforts. After exploring our dataset, we wanted to apply clustering techniques. We felt that dbScan would be a good choice since our data follows an irregular geometry. We tuned the dbScan hyperparameters to optimize the classification F1 score. We did this both for the originally imbalanced and artificially balanced versions of the dataset. We can see a clear visual similarity between the earlier PCA plot and the one currently shown. This shows that dbScan was able to accurately classify some of the articles as true or false. This is further reflected by the word correlation table shown to the right. We can see that the topics in the first cluster closely resemble topics from fake tweets. We also applied k-means to our data. We are skeptical of k-means due to our dataset's irregular geometry and the limitations of k-means. This may also explain the lack of a distinctive elbow when increasing the number of clusters. Nonetheless, we still found interesting results. We arbitrarily set k-means to find 6 clusters within the data. The table below shows the most correlated words for each cluster. Each cluster appears to correspond to distinctive topics, reflecting the diversity of subjects within fake news.
At a high level, the supervised portion of the project follows the same steps as the unsupervised portion up until the dimensionality reduction. After PCA, we prepared the data by balancing the dataset, trained multiple models using said dataset, tuned their hyperparameters based on metrics such as accuracy, recall, and F1 score, and finally visualized the results. To elaborate a little more on our methods of data preparation, we first normalized each feature of the dataset to ensure they all contributed to the classification equally. From there, we shuffled the dataset and split it into training and testing data, oversampling the fake data to maintain a balance between real and fake tweets. For model training and selection, we trained multiple classifiers which we believed would perform the best, then compared their performance. We settled on using logistic regression, linear SVM, kernel SVM, random forest, neural nets, and naive Bayes. To achieve optimal performance, we performed an individualized grid search on each classifier to best tune their hyperparameters.
The 3 best performing models were the logistic classifier, neural net, and random forest. On this slide, we can see the performance summary and confusion matrix of each model, illustrating how the random forest model performed slightly better than the logistic classifier and neural net. This slide shows a 2D visualization of the classification results. We graph each data point using the normalized first and second PCA components of that point and colorize the point based on the assigned class. The left graph shows actual true-false labels, and the right graph shows predicted labels. The graphs display an obvious visual similarity, reflecting the high performance of the random forest. In this slide, we graph the correlation between false tweets and the words within those tweets. This visualization gives us a feeling for the topics discussed within misleading tweets. The left graph shows correlations for actual fake tweets, and the right graph shows correlations for tweets we predicted to be fake. We can see that the topics discussed in actual fake tweets are very similar to the topics discussed in tweets we predicted to be fake. Throughout this touchpoint, we leveraged various types of visualization techniques to get a better understanding of how our models were behaving. Early on, we noticed that due to a much higher number of true labels in our training set, the models could simply output the same result every time and achieve a relatively high accuracy. In order to obtain a meaningful prediction model, we had to resolve our class imbalance so the models would focus on the data features themselves. Additionally, normalizing our PCA dimensionality reduced data frame generated better overall scores for our learning models. Once we had more carefully selected our data and edited our dimensionality, we ran several supervised learning models on this set and found that the random forest implementation yielded the best results. Our F1 score of 0.93 shows that our model can reliably predict fake news, and we hope this result will further inspire research into detection of COVID-related misinformation in social media. Using machine learning tools such as the one we created, platforms can quickly identify potential sources of fake news online and review these posts further to prevent the spread of misleading information.
Thank you for listening to this presentation, and this concludes our final report.